all the other talks, which I'm really looking forward to. So yeah, so what I'm going to tell you about today is a project that I've been working on for a few years now. I have a couple of papers on the archive, and for today, I'm basically going to focus on the on the third paper, the derived moduli stack of logarithmic flat connections. Okay, so my talk is broken up into 4 parts. So the majority is the first 2 parts. So I'll start just by telling you about what I'm interested in studying. Then I'll bring in some derived geometry into the picture. And then the last 2 sections, which are kind of going to be short.
Francis, can you give us a second? I think there's something with the recording. Give us just 1 second. Stop share. We'll share again. Okay, sorry about it. Should be fine now.
No problem. Right. So the last 2 sections, one of them is just about kind of a specific example that I understand better. And then at the end, I just want to indicate just a bit how I expect shifted Poisson geometry to enter into this. Okay. Okay, so let's start. So the setting that I want us to consider is the following. So we have complex vector space, C to the K, and on here we have a holomorphic function, f, and we can think of it as defining a fibration over C. And over the point 0 is a hypersurface D, which usually it's going to have a singularity. Okay, and so the goal of this project is to kind of classify or understand flat connections on C to the K that have logarithmic singularities along this hypersurface D. So before actually giving a definition, I'll just show you a couple of examples. So the simplest example is in dimension 1, if the function is just the identity, then the hypersurface is just a point. And in this case, what we're studying are linear ordinary differential equations on the complex plane that have Fuchsian singularity at the origin. So they're ODEs of this form. If we go to dimension 2, here's an example, the function x squared minus y cubed. So in this case, D is now a curve, a plane curve that has a cusp singularity at the origin. And what a connection will look like in this case is like this. So it's singular because here we're dividing by f. And basically the degrees of freedom are these matrices A and B, which are holomorphic. And in order to be flat, they need to satisfy this PDE. So E and V are these vector fields. So these are the kind of 2 examples that maybe you can keep in mind. There's many more examples that I'm interested in. For example, there's this really beautiful family of, in 3 dimensions, which I'm also interested in, but I'm not going to mention this anymore in this talk. So, okay. So here's the definition. So again, we have the function f, which defines a hypersurface D. And the first thing we can define is the top bullet point is the logarithmic tangent bundle. And this is, by definition, the vector fields on C to the K that are tangent to the hypersurface. Or stated differently, they're the vector fields such that if you differentiate the function f, you get a multiple of f. It preserves the ideal generated by f. So for a general hypersurface, this is just some coherent sheaf, which is not necessarily coming from a vector bundle. So I want to make an assumption that D is a so-called cyto-free divisor. And what this means is that this actually gives us a vector bundle. In fact, it's not just a vector bundle, it gives us a Lie algebroid. So we can kind of apply all of the usual constructions on Lie algebroids. So the first thing I want to do is take the derived complex of the algebroid. So the exterior algebra of the dual, it has a differential, and it defines a commutative differential graded algebra. If we have now a Lie algebra G, which for me will be the Lie algebra of a connected complex reductive group, such as GLN, then we can tensor it with this derived complex, and it gives us a differential graded Lie algebra. Okay. Then we can define what is a logarithmic flat connection. So it's precisely a connection d plus omega, where omega is a logarithmic one form valued in g, which satisfies the Marquetan equation. So the curvature is 0. Okay, so we can consider the space of solutions to this equation. So that's kind of the infinite dimensional space that parameterizes all of the logarithmic flat connections, what I'm calling MC of L. So if we look in degree 0, so in degree 0, we get a Lie algebra, and this is the Lie algebra of the gauge group. So this is the group that I've denoted G. They're holomorphic maps into the Lie group. And these act on connections via gauge transformations. And really, we want to think of two connections that are related by a gauge transformation as being equivalent. So meaning we want to consider the quotient space. You could just think of it as a strict quotient, but maybe more properly, some type of infinite dimensional quotient stack. So this is the moduli space of flat logarithmic connections. Okay, so this is very nice, but I guess one issue is that this is an infinite dimensional construction. And so the first goal is to find a finite dimensional model, to kind of find a finite dimensional slice for the gauge group action. So in order to do this, I need to introduce the second ingredient. So I'm going to assume now that on C to the K, I have an action of C star. It's generated infinitesimally by this Euler vector field E. And the effect of having this vector field is that all of the coordinates get a weight grading. And I'm going to assume now that the function is homogeneous with respect to this weight grading. In other words, E applied to F is RF, or an integer R. And with this now extra structure, we can define a couple of useful things that we'll use to study connections. So from the vector field E, it defines an action Lie algebroid of C acting on C to the K, and this maps into the logarithmic tangent bundle. The fact that we have this function, it means that we can take d log of F, and this is a logarithmic one form, so it defines a Lie algebroid map to C. And if you compose these two maps, you just get the projection. And this projection map, it has a splitting J, which basically includes C as the Lie algebra living over the origin, which is a fixed point of the C star action. Okay, so we have this diagram of Lie algebroids. And so when we take the corresponding moduli spaces of connections, we get kind of pullback maps going backwards. And I just want to draw your attention to maybe this top right corner. So the representations of C, those are just given by Lie algebra elements. And in this case, the gauge group action is just given by conjugation. So in this corner, we have the adjoint quotient of the Lie algebra. Okay, so this will allow us to define, well, the kind of the main definition that we want to use is what I'm calling the residue. So if we take a logarithmic flat connection, omega, we can pull it first back by I and then by J, and that defines now an element of the Lie algebra. That's what I'm calling the residue of the connection. We could also take the semi-simple part of it, and that's what I'm calling the semi-simple residue. And this is the kind of the main invariant that I want to fix. So what I denote by MCLA, that's the space of logarithmic connections where the residue is in a fixed adjoint orbit. And this is something that I'm going to be doing for the remainder of the talk. Okay, so given that we've done this, I can now tell you how do we produce one of these gauge slices. And the way to do it is the following. So we start with this semi-simple residue S, which is an element of the Lie algebra. And we can pull it back by P, and it gives us a connection for this Lie algebra there, but I'm calling P star of S. And I'm going to use that to define two spaces. The first space, XA, this is defined to be the logarithmic connections such that when I pull it back by I and then extract the semi-simple part, it's equal to P star of S on the nose. Extracting the semi-simple part is something that you can do with these connections, and I'm not going to tell you what it means. I don't have time, but So just that's something you have to accept. The second thing that I can define is what I'm calling ODEs. And this is by definition, the gauge transformations that preserve this P star of S. And this basically gives us the finite dimensional model. So the theorem is that XA is a finite dimensional algebraic variety. ODEs is an affine algebraic group that acts on XA. And we have an equivalence like this. Maybe this defines a groupoid. And here we have the groupoid of logarithmic connections. These are equivalent. Yes?
I just want to ask about the word residue.
Yeah?
Because residue of a differential is an invariantly defined thing. I will. I just wanted to ask about the residue because residue of a differential is an invariantly defined thing. And I'm just reflecting that if we took a different capital E, the residue would rescale.
That's right.
So I wonder if there's an invariant way of defining the residue.
The residue depends on really on this algebroid. The fact that you have this map.
So, and the map E.
Yeah.
So if I multiply E by 2, the residue changes. That's all.
No, it doesn't. No. I think it's going to.
Okay.
I could be wrong. I think it doesn't depend on that, but it depends on whether you change the C star action, for example. I call it the residue because in dimension 1, it literally is the residue. Yeah. Okay, so this was the kind of the first part. And now I want to talk about how do you kind of extend this to the derived setting. So kind of why you might want to do this is, for example, this algebraic variety is often singular. And another thing is that if you want to start looking for things like shifted Poisson structures, then you need kind of more space homologically in order to describe them. So that's what I want to talk about next, derived stacks. So I should say I'm not an expert on derived algebraic geometry. I'm come from a more differential geometry background. So this is something I don't understand very well. But thankfully, there is a very nice paper by these authors, which gives a very kind of concrete definition that it suffices for my purposes. So it's called the bundle of curved differential graded Lie algebras. So what this is, it's defined over a manifold M, and it consists of a graded vector bundle, which I'm calling L, which starts in degree 2 and goes up. And it's equipped with 3 structures. So number 1 is a section in degree 2, which you can think of something like a curvature. We have a degree 1 bundle map, which is sort of trying to be a differential, but it doesn't square to 0. And then 3, we have a smoothly varying graded Lie bracket on the fibers of L. And these have to satisfy 3 conditions. One is the Bianchi identity, which is that F is in the kernel of delta. 2 is that the square of this D, it's not 0, it's equal to bracketing with F. And then 3rd, we have some type of Leibniz rule for this D with respect to the bracket. So that's going to be our model of a derived manifold. And if we have a group that's acting equivariantly on everything, then we can take this to define for us a derived stack. Okay, so there's kind of 2 important things that you can extract when you have one of these derived stacks. The first is the Mohr-Cartan locus. So this is defined as the vanishing locus of that section F, what I'm calling VF. And this is preserved by the G action, so we get an action groupoid. The second thing is that if we take any point on the vanishing locus, then we get a tangent complex. And this is given by a complex like this. So in degrees 2 and above, it's just the fiber of that vector bundle. And notice here this delta, because f of x is 0, this now is a differential. Okay, then in degree 1, we put the tangent space. The map is the derivative of f. And then in degree 0, we put the Lie algebra and the infinitesimal action. Okay, so given a DGLA, there's kind of a standard way of extracting one of these bundles of curved DGLAs, and we can apply it to this DGLA. remember, this is the logarithmic form is valued in G. So we take for the base manifold to just be the thing in degree 1. The bundle of graded Lie algebras is just the trivial bundle where we start with everything in degree 2 and higher. The section is the curvature that I told you about earlier. And then the differential, so this depends on the point omega in L1. So it's D plus bracketing with omega. And the gauge group, it acts on everything equivariantly. And so in this way, we can get a derived stack of logarithmic flat connections. And just as before, I want to fix the adjoint orbit of the residue. And okay, so now we have a derived stack. It's kind of an upgrade of the one before. And we have the same problem that this is an infinite dimensional construction and we want a finite dimensional model. So that's what I'll describe now. This is maybe the most technical slides, or maybe notationally heaviest. But here's how you can do it. It's actually not that bad. So remember, we have these three structures. We have this one form, alpha naught, which is d log f. We have this Euler vector field E, and we have this semi-simple element S. And we can define three operators on the DGLA. So delta S, that's D plus wedging with alpha naught and bracketing with S. That's a degree +1 derivation that squares to 0. It's a differential. The second is we can take the interior multiplication with the Euler vector field. That's a degree -1 derivation. And then LS, that's the sum of the Lie derivative in the direction of E plus the operation of bracketing with S. And that's a degree 0 derivation. So what we can do now is we can look at the kernel of LS. That's what I'm calling LDG0. 0 is like the 0 eigenvalue. And it turns out this is a finite dimensional subalgebra, which is preserved by delta S. So we get in this way a finite dimensional DGLA. And if you look in degree 0, what Lie algebra you get, it's actually the Lie algebra of that algebraic group I mentioned earlier. The final thing is, if we kind of now take this iota E and restrict it to this LDG0 and take the kernel, we get a sub-DGLA. And this sub-DGLA, it kind of encodes everything in the sense that this DGLA is like a shifted adjoint of this one. Okay, so both of these DGLAs, they define derived stacks in the same way. I'm calling one of them WS and the other one US. And because of what I just told you, you could think of the WS one as a shifted tangent bundle of the US one. And again, I want to fix the residue to be in an adjoint orbit. That's what I'm calling W of A. So the main one that I'm interested in is W of A, but obviously this US is also important because it kind of encodes everything. And the picture to have in mind is the following. So we kind of, in purple, I drew like a tubular neighborhood of the hypersurface, and WA are like the flat logarithmic connections on this tubular neighborhood. And kind of if we just look at a fiber above 1, we get this smooth hypersurface. And US is like the moduli space of flat connections on that fiber. So the fact that WA is sort of living in a tangent bundle, that's like we're adding the monodromy. And this kind of induced projection map, that's just for getting the monodromy kind of around that tubular neighborhood. Okay, so now I can state the main theorem. So basically it says that this WA is giving us a finite dimensional model for this moduli space. So first of all, if we look at the Mohr-Cartan locus of WA, this recovers that algebraic variety XA. And there's an equivalence of derived stacks from this one WA into the moduli space. And by equivalence, I just mean the following, is that this map Q induces an equivalence of the Mohr-Cartan categories. And for every point in the Mohr-Cartan locus, we get a quasi-isomorphism. Okay, so that's the main result that I wanted to explain. Okay, so in the remainder, I just want to mention two things. So one is there's the special case where the hypersurface is a plane curve of this form. And this is a case that I understand much better. So I'll just say a little bit about what you get in this case. So there's sort of like a resonance type condition. So if the eigenvalues of the adjoint action of S are large enough in some sense, then this moduli space, it kind of has an even simpler description. And it's basically given by, you have some function B on some vector space, and you're taking basically the derived vanishing locus of that function, and you're quotienting out by a parabolic subgroup. So here's an example of one of these things. So if the group is GLN and the matrix A is given by this, then this derived moduli stack is actually equivalent to just an ordinary stack, nothing derived. It's the quotient of the cotangent bundle of the flag variety by GLN. So for when this condition on S is not satisfied, it can be a bit more complicated. Here's kind of a cartoon picture of what the moduli space looks like. For that function F, the group GL3 and that choice of the matrix. Basically, the part you can see from that derived vanishing locus is just like the red and the green, and there's this kind of extra component shooting off kind of far away. Okay. So that's all I wanted to say about that. So in the last part, I just wanted to mention the relation to Poisson geometry and what I expect to happen. This part is sort of conjectural. So for this, it's useful to go back to the one-dimensional case, and this is the case that's actually already understood. So this was work done by Philip Bolsch. So he studied the Riemann-Hilbert correspondence for basically Fuchsian ODEs on a disk. And he basically got a very nice description of what the moduli space looks like and what are the geometric structures living on it. So basically, the way to approach this is that he first of all introduces a framing at a point, say the point 1. So you get these two spaces, what I'm calling log FRA. This is a moduli space of framed log connections on a disk, which has a residue in an adjoint orbit. On the boundary of the disk, you have a circle, and on there you can put the moduli space of framed local systems. And this moduli space of framed local systems, just by evaluating the monodromy, it's isomorphic to G. So what Bolsch explained is that that this space, this moduli space, it carries a quasi-Hamiltonian structure. And so it has a group valued moment map, which is precisely given by restricting to the boundary circle and taking the monodromy like that. Okay, so this was given a shifted symplectic interpretation by Safranov. So what he explained is the following. So if we now forget the framing, which means that we quotient out by G. So first of all, on the circle, we get G mod G. And this admits a +1 shifted symplectic structure. And what I guess Safranov explained is that when you have one of these group value moment map, it descends to defining a Lagrangian map. So this operation of taking a logarithmic connection and restricting to the boundary, that has a Lagrangian structure. In particular, that means that the moduli space of unframed connections has a Poisson structure. So now if we go to higher dimensions, this is sort of the picture that I have in mind. So again, on the base, we have the disk with the boundary. If we look at the pre-image of the disk, that's a tubular neighborhood of the hypersurface, which I'm calling X. And that is a boundary, which is the pre-image of the circle, which is a manifold of dimension 2k minus 1. If you compactify it, it usually has a boundary. So that means that the moduli space of local systems, kind of by the work of PTVV, this moduli space will have a 3 minus 2k shifted Poisson structure. And essentially the idea is that you can start with a connection, define like a logarithmic connection on the tubular neighborhood, and you can again restrict it to the boundary and take the holonomy, and that should define a map. And the conjecture is that the moduli space, it should admit a shifted Poisson structure of degree 2 minus 2k. And this restriction map, it should admit something like a shifted coisotropic structure. So this is something that, very conjectural. I have like very minor piece of evidence, which is the following. So if we go again to this case of these plane curves, and we just look at a connection of the following form, a very simple form, then what I can show is that a formal neighborhood of this connection admits a -2 shifted Poisson structure. Okay, so that's everything I wanted to say. So yeah, thank you.
Thank you, Francis. Are there any questions? Yes, Theodore.
Thank you. Just I have a simple question. So the data that you described with distinguished section, playing the role of curvature and Bianchi identity and so on and so forth, they all assemble into a single homological vector field, which lives on some graded, well, actually, total space of a vector bundle. So is it maybe it's simple just to argue exactly in this language, just to consider corresponding supermanifold and work with this homological field directly?
Yes, that's true. The advantage of this maybe is that when you're working in infinite dimensions, you don't necessarily want to dualize.
Sorry, what's the difference?
Well, yeah, like you could do like, it's like if you have a Lie algebra, you can take the Chevalier-Eilenberg, and that's like what you described.
Well, it's just, yes. Mhm.
So in this case, you might not want to do that if you're dealing with the infinite dimensional case. But I agree what you said. It's exactly the same.
Yeah, but it looks all the structure that you describe actually just is a result of disassembling this homological vector field and looking at what happens in particular degree components.
Exactly.
So all those equations and pieces of data are just results. And perhaps if you work with a homological vector field as a whole, it may give you some differential geometric intuition, whether it will find dimensions or infinite dimensions.
Yes.
It's just a remark, so I don't know.
Yeah, I agree. That's exactly right. And I'm just saying the only reason I didn't want to do that is because I didn't want to dualize when you're working with infinite dimensional vector bundles.
Yeah, but people go around such difficulties. Yeah. Thank you. Yeah.
Anyone else? Anyone on Zoom, maybe? I don't have the chat window.
Yes, can I ask a question here about the last result? That the -2 shifted Poisson structure. So yeah, just wondering if that comes from a current algebroid.
I think a current algebroid would be if you had a +2.
No, a Poisson structure. A Poisson structure. It's -2. Well, I mean, depending, I guess, on what convention you said, it's +2 shifted symplectic structure.
Right. Yeah. I don't know why, but this convention is like the dual of a -2 shifted symplectic.
Ah, okay. Then it's a completely different thing.
Yeah.
Okay. Okay. Thanks for clarifying that.
Maybe time for one last question. If not, then we need to make room for the next speaker.